Alright, so I went ahead and decided to go ahead and put a short one together for another example of finding force vectors directed along a line in space. Okay, it's similar to what we did in one of the examples in the last video, but it's a little bit different and has one extra step that I wanted to make sure that was clear and pointed out to you. So here's a basic problem that we have. So we'll get into this without further ado. Alright, so in this video, we're going to take a look at how do we find a force vector that's directed along a line. And now this is useful for ropes, but can be used for anything really. It could be support reactions in unknown directions, but we're going to do this under the guise of, a rope or a cable with a force acting along it. Okay, and so this will be kind of our first real physics application to resolving some of these things. Now, if we recall from our basic relationship, the force vector F is the magnitude of F dotted into a unit vector in F's direction. Okay, and if you remember when we talked about position vectors the last time on this, we could define a position vector from A to B as being some R vector. All right, so in a general sense, what we've done is we've said, okay, I'm tying a rope at a point A, and I'm pulling on it with a force F such that A to B is now a straight line. The force that makes this straight is now acting along that line A to B. Okay, all ropes and cable problems, you're going to handle those the same way in terms of vectors. Okay, for that segment from A to B. All right, so all we're going to do then is that, the key to this is that if I know this magnitude, because that's what that is a magnitude here, okay, that we know that to get a forces vector, I needed the force magnitude times a unit vector for F. Well, the problem is I don't have a unit vector for F. What I do have is I know that a unit vector from A to B, which is this guy, that I can construct him based off of positional data. I could do a position vector from A to B to get this guy, and then I know that this has to be equal to UF. Okay, that's the key to the method that we're going to show here. Okay, so it's got this one extra step from the example that we did in the last video. Okay, so all we're going to do is we're going to find a position vector from A to B, which we're going to call as R. And again, R goes from A to B. It has a length other than 1 in most cases. Okay, once I have R from A to B, then I can use that to get U from A to B as simply being this property, vector R A to B over magnitude R A to B. Okay, and then once I have that, then I can say, well, I know that UF, UF is going to be equal to UR. That's the trick, okay? Because technically they're different vectors, but we know they have to be the same because the force is pulling on the line. So a unit vector along line AB is the same as a unit vector along line F, the line of action of F, that they're the same. That's the trick. That's kind of the subtlety of what it is that we're trying to do. Okay, so let's give one a shot real quick. Real simple example for us to look at. I have a man, awesome stick figure here, okay, sitting at B. He's pulling on a rope that's tied up at A. Okay, now what we have is we have a Cartesian coordinate system. X is out, Y is to the right, Z is up. Okay, and we know the location of where A is tied in at. Okay, that it's directly above the origin by a distance of 30 feet. Okay, and then point B we know is going to be 12 feet out in the X direction. It's going to be 8 feet over in the negative Y direction, and it's going to be 6 feet up in the positive Z direction. Okay, and so what we want to do is we want to create the Cartesian vector and calculate the directions that come out of that. All right, so let's go through and look at it. The first step is, and one tip in all of these problems is, anytime you are given dimensional information or distances, and especially in three-dimensional problems, your brain needs to go and say, all right, I'm doing a position vector. So we're going to go back and we need to come up with a position vector that I know if the man is pulling on this rope that's tied at A, then the force or the direction of the pull on this is going to be directed along that line from A to B. All right, so all I'm going to do is I'm going to first come up with the coordinates of A and B. All right, so x, y, z coordinates for A we know is 0, 0, positive 30. That's my start point. So my force vector is actually coming down this direction. Okay, and then B is going to be positive 12 minus 8 positive 6 gets me to this point. Now again, all this is this is basically a position vector from my origin up to here, or a position vector from my origin over to B. So you could say that this is R from O to A, and this is R from O to B. Okay, and if you remember, we talked about in the last one that in calculus, this is how they define points in space, is simply as a vector from an origin 0, 0, 0. Well, that's what we've done. If the origin is 0, 0, 0, that's the vector, which is the same as the coordinates. Okay, so once I have that, then all I do is find my position vector R from A to B. Okay, and remember our nomenclature is it goes from the tail to the head. And since my force is coming this way, my tail is at A, my head is at B. Okay, and so R from A to B on this is then just going to be simply B minus A for the I, J's, and K pieces of this. So 12 minus 0 is this term, minus 8 minus 0 is the second term, and 6 minus 30 is the K term. And if I do all the math, we're now at 12I minus 8J minus 24K. You now have the position vector. Okay, now, of course, this guy has to have some units. I've been kind of sloppy on units so far, but that's a foot dimension. Okay, and then once I have the vector, now I can go in and find the magnitude of RAB is that R guy, and that's just simply the square of these three terms. So 12 squared plus a minus 8 squared minus 24 squared. That's what you see here. Okay, and if I do the math, this becomes 28 feet is the magnitude. So that rope is 28 feet long. So now with the vector and the magnitude, I can now construct the unit vector for R. Okay, and so if I do that, then I just take this vector and divide it by my R. So that's going to be 12 over 28 minus 8 over 28 and minus 24 over 28 gets me these three pieces. So again, 12 over 28 times I, minus 8 over 28 times J, and minus 24 over 28 times K. Okay. All right, and so then to find the force, we know that right over here, UR is equal to UF. That's the connector. So we've got UR, and if I say that this vector is the same as the UF vector, let's put a subscript on there so we denote that they're different, okay, when they're actually the same, but just so that our nomenclature is pure on here, that if the magnitude of this force is 70 pounds, I don't think I mentioned that before, so the man's pulling on the rope with a force of 70 pounds, so all I do is I take 70 pounds and I multiply it into that unit vector, or do a dot product of a scalar into a vector, which is multiplying. So 70 times 12 over 28 gets me 30, 70 times minus 8 over 28 gets me minus 20, and 70 times minus 24 over 28 gets me minus 60 as my force vector. So my force vector is 30I minus 20J minus 60K, and the units are pounds on that. Notice that the units that show up here are the same as what's on the magnitude. The unit vector here is unitless. And that's what allows me to make a position unit vector equal to a force unit vector, because it's feet over feet, right? If that was a foot and that's a foot, they would cancel out. So unit vectors are always unitless, and that's the key to being able to come over and do this step, where I can now take a unit vector of one type of vector and compare it to a unit vector of another and do all of that. Okay, once I do that, then I can find my direction cosines by simply taking the unit vector that we had, 12 over 28, cosine inverse, 64.6 degrees, 8 over 28 negative, cosine inverse, 107 degrees, and then minus 24 over 28, cosine inverse, 149 degrees. Now again, I did some rounding on here, but roughly that's what those direction cosines would be. That's the step. So this is what you need to be able to do, is to be able to kind of follow these simple steps and to be able to set up the basic relationships. But the formulas are exactly what we've seen in the previous videos. So anyway, I just wanted to kind of toss that example in there and to illustrate what it is that we're doing. Another trick involved with these unit vectors. These unit vectors are so handy for just kind of having direction. And it's basically like, pointing and saying, I'm going that way. I don't know how far, but I'm going in that direction. That's what a unit vector is doing. Okay, so it'd be like this man pointing at, I guess if you were standing at A and pointing at B, he's just kind of pointing. He's not pointing the full distance, but he's just kind of pointing and saying, I'm going to go one unit that way, and I'm going to keep going. Okay, So that will lead us into some properties of force vectors. Force vector is also known as a sliding vector, meaning that anywhere along its line of action, I can relocate it. Okay, as long as I stay on his line, he can move up and down, and so that's what also allows me to move these unit vectors around, as they share the same line of action. But again, I don't want to diverge too much, but we'll get into that here in the coming lessons. So I hope that's made some sense to you. It's yet another example. The more that you see of these, the more that you do, the more that it will make sense, and the faster you'll get at them, and the more comfortable you'll get, and you'll be well on your way to being, a master of vectors. So I hope that's made sense to you. As always, let us know if you got any comments or questions in the comments down below, and be sure to like and subscribe to the channel and to this video in particular, and we will see you guys next time. All right, have a good one. See ya. Bye.